In 1905, Albert Einstein first presented his two postulates, also known as the Special Theory of Relativity. They would later on make predictions about the nature of space, time, mass, energy, which at that point of time and even today seems very bizarre and non-commonsensical in nature. However, they would end up creating a very successful domain of modern physics. Now, these ideas, they did not culminate in just one day. There is a certain history behind it. In this video and even in the next video, I want to talk about the ideas, the inconsistencies and the major issues which was being faced by physics at that point of time, which led to the birth of Special Theory of Relativity. I will discuss these topics in two videos. In the first video, which is today, I will talk about the Galilean Transformations. Then I'll talk about the Newton's laws of motion and how they are invariant under Galilean Transformations when you go from one frame of reference to another. Then I want to talk about the Maxwell's equations and how the Maxwell's equations predict the existence of electromagnetic radiations. Then I want to talk about how the Maxwell's equations are not invariant under a similar Galilean transformations when you go from one frame of reference onto another. So at that point of time, two major domains of physics. One, the Newton's laws, which successfully explained mechanical behavior. Another, the Maxwell's equations, which explained electromagnetic behavior, showed a certain inconsistency under Galilean transformation. I'll end the video by talking about how to make sense of these inconsistencies. In the second video, I want to talk about the concept of ether and absolute frame of reference. Then I will discuss in detail the Michelson-Morley experiment, which successfully failed to prove the existence of an ether. And then we will carry forward from there. So let's begin. Before Einstein, the concepts of space and time were described by Galileo and Newton. Now, the Newton's laws of motion are valid in the inertial frames of reference only. Now, what are inertial frames of reference? These are those frames of reference which are either at rest or moving with uniform velocity, to put it simply. Now here I have two inertial frames of reference, S and S dash. Now let's suppose for the case of simplicity that both these two inertial frames of reference are aligned in exactly the same way. That means the axes are parallel to their respective axes. It means the x is parallel to x dash axis, y is parallel to y dash axis, and z is parallel to z dash axis respectively in three-dimensional space. Also, let's assume for the case of simplicity is that at time t is equal to 0, both these coordinate frames of reference coincide. That means O and O dash coincide at time t is equal to 0. But one of the frames of reference, S dash frame of reference, is moving with uniform velocity v along the x-axis. So after some point of time, this second frame of reference will have moved ahead with respect to the first frame of reference. Now, if I have two observers, both in each frame of reference, and they have synchronized clocks and synchronized measuring rods, and they look at a given particular physical event, then their measurements of that physical event will be related by what is given known as the Galilean transformations. In the Galilean transformations, the position coordinates in a direction which is perpendicular to the direction of motion will remain unchanged, and the position coordinate in the direction where the motion of the frame is taking place, x dash will be equal to x minus vt, where v is the velocity and time is the time period which has elapsed. Now in Newtonian physics, the concept of time is absolute throughout the universe, in the sense that if there are two observers and they are both moving relative to each other with certain velocity, then if they measure the time period between two physical events, it doesn't matter how fast one is traveling or how slow one is traveling or whether or not both of them are at rest, they will both measure the time period difference between two physical events to be exactly the same. In a way, it is saying that time flows in the same manner for all observers in the universe. Now, the Newton's laws of motion are valid for both these two observers. That means the Newton's laws will retain their form and expression for both these two observers, even though one is at rest and the other is in motion. Let's see how that happens. So let's suppose in the S dash frame of reference, the observer is looking at a physical event and he concludes that the Newton's law expression is given by F dash is equal to ma dash, where F dash is the force that he measures in his frame of reference, a dash is the acceleration that he measures in his frame of reference. And for the sake of simplicity, let's assume that this acceleration is only happening in one axis, which is the x dash axis. Now, if you substitute a dash with d2x dash by dt dash 2, then you can use the Galilean transformations x dash is equal to x minus vt, where v is a constant and t is equal to t dash in the derivatives, and you can simplify it in this particular manner to m d2x by dt2, which is nothing but ma. That means f dash is equal to ma dash is equal to ma, which is nothing but the force in the first frame of reference. Now, what does this mean? This means two things: that both these two observers looking at the same physical event will conclude that the forces involved are exactly the same. They will also conclude that F is equal to ma and F dash is equal to ma dash hold true in their own frame of reference. That means the Newton's law, the form of the Newton's law, remains invariant for either of those two observers. This is what it means, that the Newton's laws of motion are invariant under a Galilean transformation when you go from one inertial frame of reference to another. What does this signify? It signifies that the Newton's laws of motion remain the same. They are invariant. They retain their form and expression across all inertial frames of reference. This means that this physical law is universal in nature for all inertial frames of reference. This is a good thing because observers across an infinite number of inertial frames of reference can use this universal law to explain mechanical behavior. It also suggests that there is no absolute frame of reference. As far as Newton's laws are concerned, all inertial frames of reference are equivalent in nature. Now, can we make the same conclusions for the laws of electromagnetism and more specifically the Maxwell's laws? Let's get into it. These equations describe the behavior of charges at rest, charges in motion, electric fields, magnetic fields. Now here I have written the Maxwell's equations in vacuum where there is no presence of charges or electric currents. The first and second Maxwell's laws tells us about the divergence of the electric field, the divergence of the magnetic field, and the second and the third and the fourth equations tells us about the curl of the electric and the magnetic fields respectively. Now I will not go into detail about the physical meaning behind each individual equation. Rather, what I'm interested in is whether or not they retain their form as you make a transformation from one inertial frame of reference to another in the same way that Newton's laws did. But before we do that, let's look at a very simple prediction of these Maxwell's laws of equations. So if you look at the left here, I have taken the curl of an electric field. Now, if I take the curl of an electric field, the curl of an electric field is given by the second Maxwell's equation. So I have written minus dB by dt in the right hand side. Now, if you are familiar with a vector calculus, del operator simply is the derivative with respect to x, y and z coordinates. So the curl of an electric field or the curl of any vector field can be written as the gradient of the divergence of that vector field minus the square of the del operator of that particular vector field. If I do that, and on the right hand side I get minus del by del t of del cross b. Now the gradient of the electric field is 0 as it's shown here in the Maxwell's equations. So I take this out, I'm left with minus del square E is equal to minus d by dt of del cross b, which is nothing but the fourth Maxwell's equation. If I substitute these values, make certain rearrangements, I get this equation: del square by del t square of E minus c square del operator square E is equal to 0. similarly, I can also substitute the values of B here, so del cross B, and I can make similar sorts of substitutions and come up with this equation that I've written here. Now, what is the meaning of these two equations? These equations are nothing but the wave equation, which is similar to del square y by del t square minus c square del square y by del x square is equal to 0, because the del operator here simply signifies that it is in three-dimensional space. It is the second order space derivative having both x, y and z components. Now, these equations predict the existence of electric and magnetic disturbances which travel through vacuum at the speed given by c. Now, as you can already see here, that the Maxwell's equations already tells us that whenever there is a time derivative of magnetic field taking place, it will always lead to the presence of an electric field, and whenever there is a time derivative of an electric field existing, it will always lead to the presence of a magnetic field. So how do these disturbances travel through space? If you have an electric field which is changing with respect to time, then that electric field will lead to the presence of another magnetic field which is also changing with respect to time, and that magnetic field will lead to a subsequent electric field which is changing with respect to time. Now, these disturbances in the electric field and the magnetic field sustain itself one onto one, and then these disturbances travel through vacuum at the speed given by c. Now, these electromagnetic oscillations or radiations is nothing but light itself, the light that helps us see the world around us, the light that reaches our eyes and gives us an image, and it helps us in mapping the world that exists around us. Now, when we talk about light and light which is traveling with the velocity of c, there is one question which is very important, and let me mention a few notes here before we proceed further. Now, the speed of light or the speed of these electromagnetic disturbances as they travel through vacuum or as they travel in empty space is given by c, which is numerically equivalent to approximately 3 × 10⁸ meters per second. Now, what is this velocity with respect to? Because if you look at the Maxwell's equations introduces this constant, but it does not tell us about the nature of the source of these disturbances. If the source which caused these disturbances was moving at a certain relative velocity, would that constitute or would that change the velocity of the effective radiation that was emitted by the source? What I mean to say is that what is the velocity of the light with respect to? Now, at that point of time, whenever we studied waves, we usually studied waves with respect to some sort of a medium. For example, if you look at the waves propagating on the surface of a pond, now you can calculate the velocity of those waves moving on the surface of a pond with respect to that pond itself. If you look at longitudinal oscillations in air, which constitute sound, then you can look at the velocity of those sound waves with respect to the propagation medium of still air. Now, if you look at electromagnetic oscillations or light traveling through vacuum, what is the propagation medium? Now, at that point of time, it was assumed that there was a propagation medium called ether. Now, ether is some sort of a invisible, absolute medium which permeates all of empty space, and electromagnetic disturbances travel through ether. Now, an important question arises. So, the velocity of light, if it is with respect to that ether, then the velocity of light should change when we look at it with respect to some other inertial frame of reference. Now, does it suggest the existence of an absolute frame of reference? Does it mean that the conclusions that we derive from Newton's laws, that there is no absolute frame of reference, all inertial frames of reference are similar, is not correct? So, to prove that, let's first write down the Maxwell's laws of equations and try to transform them from one inertial frame of reference to another, and then see if they retain its original form. Now, to transform the Maxwell's equations from one inertial frame of reference to another, first we have to do two things. Since the Maxwell equations consists of both electric and magnetic fields, and they also contain derivatives, first we need to transform the electric and magnetic fields from one frame of reference to another, and then we need to transform how the derivatives change when we go from one frame of reference to another. So now what does it mean? It means that, let's say for example, if I have a charged particle which is at rest with respect to me, then that charged particle is going to have an electric field, but it is not going to have a magnetic field. But if there is another person who is moving with some relative velocity with respect to the charged particle, then for that person the charged particle has some relative velocity. So the charged particle is going to show not only electric field but also magnetic field. So this means that the electric field does not necessarily retain its value when you look at it from two different inertial frames of reference. So we need to see how the electric and magnetic field transform as you go from one inertial frame of reference to another. Now to find this out, we make use of the invariance of the Lorentz force. Now if you remember, when we were talking about the Newton's laws of motion, we saw that when two inertial frames of reference looked upon a given physical event, the forces were exactly the same. That means F is equal to F dash, and we are going to make use of that. So let's imagine that we have two frames of reference, S and S dash, and there is some charged particle Q present in the frame of reference, and if the charged particle is moving with respect to, let's say, the x-axis with some velocity, let's suppose vq, then what is the force experienced by the charged particle due to the presence of two electric and magnetic fields in either frames of reference? Now, since we are talking about three-dimensional space, just so that we simplify these calculations, let's take a very particular example. So let's suppose that we have an electric field which is going in the y-axis, and we have a magnetic field which is going in the z-axis. And let's also suppose, for the case of simplicity, that the electric and magnetic fields are only functions of x and t. Now in that case, if a charged particle is experiencing an electric field and magnetic field, then the force experienced by the charged particle is given by F is equal to q E plus VQ cross B. If I write the components separately, I can find out that the charge experienced can be written in this particular manner, which, as it is seen here, is only existing in the y-axis. Now this is the force experienced by the charged particle in the S frame of reference. What about the force experienced by the charged particle in the S dash frame of reference? In this case, I write that the electric fields are E dash and B dash, and the VQ dash is the velocity of the charged particle in the S dash frame of reference. Now if I use the Galilean transformations, by taking the time derivative of x dash is equal to x minus vt, I can write the velocity addition theorem, which simply states that VQ dash is equal to VQ minus V, where VQ dash is the velocity of the charged particle in the S dash frame of reference, VQ is the velocity of the charged particle in the S frame of reference, and V is the velocity of the S dash frame of reference with respect to the S frame of reference in the x-axis. So if I make this substitution in VQ dash here, if I make this substitution here, so, and since I've already applied the invariance of the Lorentz force law, then I can separate these components of E and E dash and B and B dash, and then I come up with these two transformations. So this is a transformation when I make the substitution in of VQ dash, and this is a transformation that I'll obtain if I make the substitution of VQ. So E is equal to E dash plus V B dash, B is equal to B dash. So that means when I go from one frame of reference S to S dash, then the electric fields and the magnetic fields measured by two observers in these two respective frames of reference can be given by these two transformations. Now let's take the case of the fourth Maxwell's equation, which is the curl of the magnetic field. Now if I want to show that all the Maxwell's equations are invariant under a Galilean transformation, then I will have to prove it for each individual case. But if I show that even in one case it is not invariant, then I can automatically conclude that in general the Maxwell's equations are not invariant. So let's start with the most simplest case. Let's take only one Maxwell's equation and let's simplify it so that we only look at the components in the one axis, so as to make our calculations a little bit simpler. So I take the fourth Maxwell's equations, which is the curl of the magnetic field is equal to 1 by c square del E by del T. Now I have taken a very specific case where I have taken the electric field to be in the y-axis and the magnetic field to be in the z-axis. If I apply that case here, so del E by del T simply is del E by del T in the y-axis, and the curl of the magnetic field simply transforms into minus del B by del X in the y-axis. So this Maxwell's equation in for this particular case of electric and magnetic field, transforms into del B by del X is equal to minus 1 by C square del E by del T. Now what we want to see here is that since this is here we have B, E, X and T, that means this is the Maxwell's equation in the S frame of reference. So this is the Maxwell's equation which is being observed by the observer in the S frame of reference. Now I want to transform the B and the E to B dash and E dash, and I also want to transform from X T to X dash and T dash. So to make that transformation, first we'll have to look at the transformations of the derivatives. So to look at the transformations of the derivatives, we make use of the chain rule. So I write del B by del X as del B by del X dash by del X plus del B by del T dash by del X, because B is only dependent upon X and T, and obviously it's also dependent upon X dash and T dash. Similarly, I also write del E by del T as del E by del T dash by T dash by del T plus del E by del X dash by del T. Now I can automatically obtain these partial derivatives by looking at the Galilean transformations. So the Galilean transformation tells us that X dash is equal to X minus Vt. So what is del X dash by del X? If you look at the equation, it will automatically come out to be 1. So since X dash is equal to X minus Vt, del X dash by del X will automatically come out to be 1. Similarly, del T dash by del T will come out to be 1 because T dash is equal to T. And del T dash by del X will come out to be 0 because T and X are independent variables. Similarly, del X dash by del T will come out to be minus V because X dash is equal to X minus Vt. So if you take the time derivative, you end up getting minus V. So if I substitute these 4 values in these particular expressions, then first of all del B by del X becomes del B by del X dash. Now as I have already proved that as we go from a S to S dash frame of reference, B is equal to B dash, so I can substitute B dash here, so I end up getting del B dash by del X dash. So that means del B by del X is equal to del B dash by del X dash. Now if we look at del E by del T here, and if I substitute these values, then I end up getting del E by del T dash minus V del E by del X dash. Now let's put the values of the transformation of E from one frame of reference to another in this equation and see what we get. So now we substitute E is equal to E dash plus VB in the equation that we just now obtained. Del E by del T is equal to del E by del T dash minus V del E by del X dash. If I make these substitutions, then I get this particular expression. So now if I write the Maxwell's equation that I started with, which was del B by del X is equal to minus 1 by C square del E by del T, I can write del B by del X as del B dash by del X dash as we just now saw. And if I write del E by del T, this entire expression here, then I see that the nature of the expression is not exactly the same as this first expression. So basically, the fourth Maxwell's equation in one dimensions in the S frame of reference is this, and the similar Maxwell's equation in the S dash frame of reference is this. They are not the same. I mean, del B dash by del X dash is equal to minus 1 by C square del E dash by del T dash, but there are these extra terms here. So as you can see, the Maxwell's equation has whatever form it has in the S frame of reference. In the S frame of reference, the form that it has in the S dash frame of reference is not the same. Now this constitutes a very big problem, because it suggests that if there are two observers in two different inertial frames of reference and they are both studying some sort of an electromagnetic event, then both of them will have to use two different forms of Maxwell's equations. That means if there are an infinite number of inertial frames of reference, there are going to be an infinite variations of the Maxwell's equations. This gets rid of the idea of the universality of physical laws. This is a big problem because all these observers who are in different frames of reference studying the same phenomena cannot agree upon the basic laws using which they are studying this phenomena. So the fact that the Maxwell's equations are not invariant, that means they do not retain the same form and expression when we go from one frame of reference to another constitutes a huge problem in physics. Now, what could be happening here? There could be many explanations for this. Maybe the Maxwell's equations are wrong. Now, it does not seem likely because Maxwell's equations are some of the most successful equations coming from a very successful domain of physics, which is that of electromagnetism. It successfully explains the behavior of stationary charges, currents, magnetic fields, and the existence of electromagnetic waves. So this option does not necessarily seem to be very attractive. Maybe the Maxwell's equations are correct, but they are only correct in some preferred frame of reference. Now, as I mentioned earlier, that the velocity of light could be with respect to some preferred absolute frame of reference, which is the medium of ether. Maybe the Maxwell's laws of electromagnetism are only valid in this preferred absolute frame of reference, and we need to modify the Maxwell's equations a little bit so that they remain invariant as you go from one frame of reference onto another. Or maybe the Maxwell's equations are in fact correct and are invariant when you go from one frame of reference to another. What is wrong here are the Galilean transformations themselves. Now, I'll talk about this in more detail in the second video, where I want to discuss the concept of ether and the experiment performed by Michelson and Morley, where they tried to determine the changes in the velocity of electromagnetic radiation as it is traveling in two different directions with respect to the ether. So to give a summary of what we have discussed in today's video is, on one hand, you have a very successful domain of classical physics, which consists of Newton's laws or some equivalent formulations, and these Newton's laws are same for all inertial observers in inertial frames of reference. That means these Newton's laws cannot distinguish between two different inertial frames of reference. There is no absolute frame of reference whatsoever, and these Newton's laws are universal for all observers in all inertial frames of reference. On the other hand, you have these Maxwell's equations of electromagnetism, which undergo change the moment you go from one frame of reference onto another. That means they are not invariant under Galilean transformations. They also seem to suggest the existence of an absolute frame of reference. So these two very successful domains of physics seem to show a certain inconsistency when it talks about the idea of physical laws being universal across all inertial frames of reference and the suggestion of absolute frames of reference. What is happening here? So in the next video, we'll talk about the concept of ether, and in the third video, I'll introduce the final suggestions coming from Albert Einstein himself in his postulates of special relativity. That's it for today. Thank you very much.